So now we will be moving on to the topic of perms and cons, permutations and combinations. And before I get started on some of the content, I want to just disclose sort of the structure of this topic in my channel. There are so many different question types, and so I'm going to leave those to a separate video of my practice videos on practice questions explaining the common type question types. And so in this video I'm just going to explain some fundamental parts that you just need to know before you barrel into those. So certainly don't watch this video and expect to be able to do all the problems just from this video. I do believe you should also watch some of the stuff in the common question types as well. But then again, you may want to just go into questions cold, and that's up to you. So I'll get started now. So permutations and combinations, it's all to do with the ways elements of a set can be selected. So perms and combs, it's all about selection. And generally the selections are done without replacement, and however an exception may be an example where you will hopefully be able to recognise similar problems in an example. Say a padlock with 3 digits, and obviously there are 10 possibilities for the first digit, 10 possibilities for the second, and then 10 possibilities for the third, rather than 10 times 9 times 8, if you know what I mean. This would be without replacement, and that's what most things in perms and combs will be. And you'll hear this a lot, but permutations are when the order matters, and combinations are when the order doesn't matter. And so this is, and I think it's important to give other words that will help you understand this notion. So think of permutations as arrangements of objects, and combinations as just picking the objects. So, for example, like, say people are lining up, then the order does matter because you're lined up in a queue. But say you're picking a sports team, it doesn't really matter the order you pick it in, because, I mean, you're just picking the people to be on the team, if you know what I mean. And so we'll just get straight started into permutations. And say, let's imagine you're lining up 10 people. So like, these are like, these rectangles I've just drawn are spots in the queue, and then we have each person. And notice how, if we just go along this way, imagine how in here, for the first spot, we have 10 possibilities. And so any one of them could be up here. But now when we move to the second one, now we only have 9 possibilities. And then 8, then 7, then 6, then 5, then 4, then 3, then 2, then 1, right? And this is what's called the factorial function. When you multiply So the factorial function is the product of all positive integers less than or equal to the given positive integer. So that means a certain number factorial means you multiply that number by all the whole numbers below it down to 1. And so we write this as something like x factorial would be x times x minus 1 times x minus 2. And then we do a dot times 3 times 2 times 1, something like that. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, which is 720. And then 10 factorial is equal to 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 3,628,800. So that's very basic ordering up people. But what if we only wanted to, out of these 10 people, arrange 3 of them in a line? And if we only wanted to focus on the first 3, we'd only be doing 10 times 9 times 8, right? But how can we generalize this? Because imagine if we had like so how can we generalize this? So what relationship does this have to factorials? And I think I'll just give it away. If we did 10 factorial, it'd be like that. But in order to just get this, we'd just divide by all this, right? Which is itself 7 factorial. So we've done 10 factorial over 7 factorial. And what's the relationship, and how can we include the fact that we're only trying to arrange 3 people? Well, 7 is just 10 minus 3. And this is how we get our formula of n factorial over n minus r factorial. And this defines the permutation function. Total number of people, number of spots. Now here's an important note. If we did r equals n, we'd get, and 0 factorial, you might wonder, that must be 0, right? But no, it's not. Imagine, how many ways can you arrange 0 objects? The answer is 1. There is 1 way to arrange 0 objects, so this would just be equal to n factorial. And by the way, having 0 factorial equal 1 is absolutely vital to a lot of maths, so yeah. But it's helpful to think that there is one way to arrange 0 objects. This function can be done on a calculator, by the way. And this can also be done for arrangements of letters. So like the word stern, there would be 5 factorial ways of arranging those 5 letters. But say it asked how many 3-digit words could you do? You would do 5p3. And on your calculator you'd do that and you would get 5 times 4 times 3 is 20 times 3, which is 60. But what if you had a word like needless. Oh, well, we can... Not needless. How about start? If I were now to write that again, S-T-A-R-T again, would you call that a different arrangement? I wouldn't either, but one could argue that you swap the T's around. So that's why when we have repeated letters, we must account for that overcounting. So think about for every different arrangement, we're going to have however many times we can swap those T's around overcounted. So what we will do is we'll do 5 factorial and we divide it by 2 factorial to account for those T's. That would be 60. Now for an example like needless, we've got 8 total, but we have 3 E's and 2 S's. And that would equal 3,360. Now those are some fundamental ideas. For the most part with permutations, I'll leave the rest to my next video and your own practice, but just a few key ideas about how to handle other things when it starts being restricted, because these are all unrestricted. Like, there aren't conditions like, oh, the R and the N must be together or stuff like that. But I'll just go over a few helpful strategies. Diagrams. Like, say it wanted the R and N together, like, I would be doing something like this to see if I can visualize a way of solving it. Sometimes splitting into cases is very helpful. Like, for example, like saying, especially when there are repeats involved and you have to be very careful about overcounting. An example would be something like, how many 3-digit numbers from 1, 2, 2, 3, 4, 5 when each is used at most once. Here I would split into the cases. Case 1, no 2s. Case 2, 1, 2. And then I'd go from there. And then things like words like not. So like if it said arrangements of needless with E's not all together, it would be hard to just do an exhaustive way of adding up all the different permutations of that, because remember, you could have all the E's separate, or you could have 2 of them together, and so on. So instead, what when you have something like that, you would do total arrangements minus arrangements when they are and another thing you need to be cautious about is the use of and versus or. And is when you would multiply. And or would be when you add. And so, for example, like saying needless, saying it needs to end in a vowel, and the S's must be separate. So what you'd do is you'd find the considerations for each condition and you would multiply them. But say you had 1, 3, 5, 7, and then you had to do make 3-digit numbers out of that, ending in 5 or 3. Then what you would do is you would do the number of numbers that end in three, and then you'd add that to the number of numbers ending in 5. So we will leave combinations to the next video.